Hey, hello, welcome back. Today's lesson is going to deal with the problem-solving process. This is something we do a lot of, but we have a lot to think about as we do our problem solving. So let's get started by asking the essential question: how do we solve specific technical design problems? Here's another problem-solving process that's a little bit more detailed than the one we looked at in the last lesson. And the first thing that we normally have to do when we're dealing with trying to solve a problem is we need to identify and define the problem. Now that may seem pretty easy most of the time, but sometimes it isn't. If you're dealing with a very complex mechanical system, sometimes you know something's wrong, but in order to try to find exactly what's wrong can be a problem. Think about trying to diagnose a problem in a car. So you know what the problem is. You have to analyze the problem. You got to think this through and try to figure out exactly what's wrong. You have to identify possible solutions to that problem. Sometimes that problem can be solved by brainstorming. When you brainstorm, you throw out as many ideas as you can as quickly as possible. Many of those ideas are really not very feasible, but they do help you come up with better ideas. You select and plan the solution. You implement the solution. Basically, you go through with it, you make it, you do what you need to do, and then when it's done, you evaluate it. If it's working great, everything's solved, but a lot of times you just continue to refine it and see how you can make it better, and this is how we end up with the technology that we have today. It's a non-stop continuous process. So we have a problem-solving activity that's going to relate to this. It's going to be one of our larger projects that we do for the year, where you're going to be over in the materials lab engineering a solution to it. And the basic problem is design a vehicle to travel as far as possible using wind to propel the vehicle. Now right now I know a lot of you guys are probably thinking crazy ideas, but there are rules and regulations to this project, and many of those will be discussed in more detail in the project handout and in class. But first off, just think we're basically using a rubber band. The power for this vehicle must be supplied by a rubber band provided. We can give you all the materials for this, but I also encourage you to go out and find your own materials that you may want to use for this activity. We will be supplying the rubber band that we are using to test in class. However, if you decide that you want to work on this a little bit at home and you want to test your vehicle out, by all means go to Staples or Office Max and buy some number 64 size rubber bands. They're approximately 1/4 of an inch wide and about 3.5 inches in diameter. So those are the rubber bands that we're going to use. For complete details on the activity, I will refer you to the activity sheet for this project. So let's see what we need to think about with this project. And remember, we always try to address this as a STEM approach. So here's the science in our STEM project. How do propeller blades move an object, and why are house fan blades shaped differently than airplane propeller blades? Here are two examples of fan blades. This would be a fan that you would commonly see in a little fan that's sitting in your house to move air around. Here would be an airplane propeller. Notice that they're entirely different. House fan blades are wide, many of them. Airplane propeller blades, not as many, much narrower. It's like, gee, what's the difference? What are we trying to do? Well, let's talk about air pressure, because this whole project relates to air pressure. Air pressure is a force exerted by air. Air pressure varies around the globe and at different altitudes, at different heights. A low air pressure means that air molecules are further apart, while high air pressure means that air molecules are closer together. Alright, so what does that mean? Let's say you're at a swimming pool, and you're swimming around on the surface of the swimming pool, and you're slightly under the surface. You don't really experience a lot of pressure from the water because you're at the surface. But if you dive deeper, there's going to be more and more pressure exerted on your body by the water pressure. Think about whenever they go deep sea diving, go down to the Titanic at the bottom of the ocean. They need to be in a special vehicle that can handle the handle the water pressures. Air responds just like that. When you're down standing at the beach at ocean level, the air pressure is going to be higher. The molecules are going to be more pressed together. As you climb higher into a mountain, there'll be lower air pressure. The molecules will be further apart. You'll experience it by being harder to breathe. Even if you're cooking, if you're reading the instructions on a box of macaroni and cheese, there'll be special instructions for high altitude cooking, because things are going to cook differently at higher altitudes. So just remember, the air pressure drops the higher you climb in altitude. Now, we have a couple of scientific facts to deal with here. There's a principle out there called the Bernoulli Principle. And what Bernoulli said is that if we increase a fluid's speed, the pressure will decrease. And a dude by the name of Venturi came up with the Venturi effect, the reduction in fluid pressure that results when fluid flows through a constricted section of pipe. Alright, so what does all of this mean? We're basically saying that if we speed up the air, the pressure will decrease. And if we also force a fluid, in this case air, through a restricted area, meaning we start out with like a piece of pipe that's large in diameter going down to a smaller diameter pipe, we're going to speed up the air, we're going to change the air pressure, we're going to reduce the air pressure there as well. So here are a couple of examples. Let's say you have an airbrush. Those are those special paint brushes that hook up to compressed air. They use them to paint t-shirts and do detailing on cars, and even an air pressure gun for painting a car. They work off of the Venturi effect. So here you see a bottle with paint in it and a tube that goes up, and we blow air across the top of that straw. You can get the same effect by blowing air across the drinking straw. If you blow enough air pressure through there, you're going to reduce the air pressure at the top of the straw. Well, less air pressure at the top of the straw, more air pressure down at the bottom of the straw. It's always going to try to find an equilibrium. The fluid is going to travel up the straw because of that pressure difference, and then it gets interspersed with the air to give you a fine effect for painting. Let's look at a carburetor on an engine. Now, most cars today are made without carburetors. Older cars have carburetors, and lawnmowers have carburetors. So let's say this is a carburetor on a lawnmower. We draw the air in through the engine at a wide area, and we make it smaller. Okay, when we restrict this pressure, or restrict this area in here, the air molecules speed up, the molecules spread apart. We have low air pressure in this tube. Because of the fuel system being a higher pressure, the fuel is actually drawn up into the tube and into the carburetor chamber, and it mixes with the air, and that's how we get an engine to work. Here are a few more examples where we use pressure differences in everyday life. Here's a chimney on a house. Higher altitude, less pressure at the top of the chimney than at the bottom. Air is just naturally going to want to flow up this chimney. So when you light a fire, the smoke goes up the chimney. This is something that's in conceptual form right now. I don't believe any are really built, but this is a new device called a solar chimney. And if we build these in regions where we have a lot of temperature and open spaces, imagine glass in all of these spaces at the bottom of this area, like a greenhouse. This is just a 3D computer model built right now. But you have a greenhouse effect in here. You're heating the air because of the pressure differential at the top and the bottom of the chimney. You're causing a high volume of air to flow up that chimney. Well, if we stick an electrical turbine with a fan blade on it, all of that air going down up through that chimney will cause that electrical turbine to spin quickly, and this will generate electricity with very few moving parts. Very, very cheap way to generate electricity. Great concept. Let's talk about nuclear power plants. Imagine this for 3 Mile Island. This little dome here is the reactor building. This is a cooling tower. Basically what happens is we draw water in from the river. It's used in the reaction to keep things cool. The water is not radioactive, but it's too hot to stick back in the river. So they put them in pools at the bottom of these cooling towers, and because of this unique shape of the chimney, we draw maximum airflow across that pool of water straight up the chimney to cool that water before we can put it back in. Now, most nuclear reactors only require 1 cooling tower per reactor. At 3 Mile Island, we have 2 reactors on 3 Mile Island. One doesn't work anymore, but there are actually 2 cooling towers for each reactor building. And you're thinking, well, why is that if we really only need 1 per each? The reason being is they could not make the chimneys as tall as they needed them to be on 3 Mile Island. Because they could not make them as tall, they needed 2 to actually get the same cooling effect of 1. Why couldn't they make them as tall as they needed them to be? Because of Harrisburg International Airport. They didn't want to make them too tall and have an airplane fly into them. And even in your house, your attic, you have a cooling effect with air pressure in your house. Because the air gets hot in your attic, you need to get that hot air out of it. Usually on most houses today, there's going to be either a gable vent, a little vent on the end of the roof, or there'll be what they call a ridge vent, a vent going along the top of your roof that lets the hot air out. Well, to let cooler air in, this area outside your house called the soffit, the place where your rain gutter hangs, if you look around on most houses, there'll be ventilated holes in that soffit region, and that lets cool air in as the hot air exits. Then that keeps moisture stabilized and temperature stabilized in your house. So some neat examples of using pressure difference. So let's go back to this whole thing about the fan. A house fan is designed to push a large volume of air at a low speed than an airplane propeller. Also, the shape of an airplane propeller is more like an airplane wing to develop higher pressure differences to pull the airplane. Both shapes produce a pressure difference. So yep, both of these things create pressure difference, but because house fans are made with cheap electric motors that don't have a lot of power and don't run very fast, we basically need a big fin to be able to push a large volume of air. We don't want that box fan sitting in your living room to take off like an airplane. However, airplanes, we can spin them pretty quick with a high power motor, and we can create a different pressure difference. What are you going to use in your air-powered car? Well, that rubber band's not very powerful. Our fans are probably going to look more like this than like this. Alright, so air pressure on a wing. So let's talk about how air pressure affects an airplane wing. Okay, so here's your airplane wing. If you notice, airplane wings are going to be more rounded on top and flatter on the bottom. Because of that, as the air hits the front of this airplane wing, the air traveling across the bottom of the wing just travels pretty straight, meaning the air pressure doesn't really change a whole lot. Because the air pressure has a longer distance to travel over the top of it, the air molecules spread out, meaning it creates a lower air pressure. Less pressure on the top of the wing, more on the bottom. It creates lift. It actually pushes that airplane wing up. And that's what lift is. That's how it affects an airplane wing. So how does that affect an airplane propeller? Well, here's a cross-sectional view of an airplane propeller. Okay, so if you look at this airplane propeller, if you were to cut this airplane propeller at this point, you'll have a flat section along the back and a rounded corner along the top. And as you go out through, you'll continue that effect. So as this propeller spins, the air in front of the propeller has a longer distance to travel, less air pressure in front of the propeller. More behind it, it pulls your airplane through. So as a quick review, here's how all the STEM works in this project. The science behind it is the air pressure, the Bernoulli Principle, Venturi effect. We also have to worry about friction and mass on our vehicle. So friction in the form of the wheels not being able to turn, friction in the propeller assembly, and of course how heavy is your car. The technology and the engineering in our STEM. You're going to design, draw, and you're going to construct a vehicle for testing. And the math, you're going to do some calculations to build your vehicle, measurements on the vehicle, and you're going to do some distance measuring and some averaging. Now, what we're going to do is you're going to refer to the activity handout for some more specific detail. When designing your vehicle, ask yourself these couple of questions as you're working through this activity. Will weight play an important role in the performance of your vehicle? Do you think you want your car to be heavier or lighter? What size and type of wheels and axles do you want to use? Obviously, more friction in your axles and your wheels, the slower your car is probably going to go. Do you want to steer your vehicle? Now, we're not going to be driving it around corners or anything, but you do want your car to go as straight as possible. Meaning, if you build your car and you can't adjust your wheels and they're a little crooked, you're probably going to run into the wall and not get a very good distance out of your vehicle. So we'll talk about how we can make adjustments as you test your car. Do you want to angle your propeller shaft, or do you want to keep it horizontal with the floor? All these things have some different effects. And are you following all the rules and size requirements? Because yes, you are graded on how well you follow the rules. Now, when you're trying to determine your wheel size, we're going to take your car and we're going to draw it out on a piece of graph paper. So you're going to draw it out full scale. Well, you're allowed a propeller diameter maximum of 11 inches in diameter, meaning from the axle down to the bottom of the blade is about 5.5 inches. If you don't design your car high enough, you're going to be slapping that thing into the floor. So, you have to think about your design. You have to think about the actual wheel radius, the frame height. I would say from the propeller shaft to the ground should be about 6 or 7 inches for enough clearance. And remember, we do have size limitations, not just because I don't want you to build a car bigger than this, but we have to store them in the lockers in the materials lab. And we have maximum size limits to deal with that. And that's the end of this presentation. We'll talk more in class about the actual project itself. Good luck.